Hello viewers, welcome to today's lecture on multiplexing applications. This is the second lecture on multiplexing applications. In the last lecture, we have discussed about the telephone network and the DSL technology, which are very important applications of multiplexing. In today's lecture, we shall consider two another important applications of multiplexing. One in cable modem, and we shall see how the conventional cable TV network has been extended to provide internet service, and also we shall see how multiplexing is used in SONET network. So, here is the outline of today's lecture. First, we shall consider the standard cable TV system, the frequency bands used in it, and various devices used in cable TV system. Then we shall discuss the extension of cable TV system into a new network known as hybrid fiber coaxial network, or in short HFC network. We shall discuss how the bandwidth is distributed and how the bandwidth is shared between upstream and downstream data, so that you can have internet service. Then we shall consider SONET, the synchronous optical network. Here we shall see the different types of devices used in SONET network, and the STS, the synchronous transport signals, a hierarchy of signal levels used in SONET network. We shall discuss about SONET frame format. And on completion of this lecture, the students will be able to explain how distribution of TV signals take place in the traditional cable TV system. They will be able to explain how HFC, that hybrid fiber coaxial cable network, allows bidirectional data transfer using cable modem. They will be able to state the data transmission scheme used in cable modem, and so far as the second application of multiplexing is concerned, they will be able to explain the operation of SONET network. They will be able to explain the function of different SONET layers. As we shall see, there are 4 different layers in SONET network, and they will be able to specify the SONET frame format. So, here is the traditional community antenna TV network, or commonly known as CATV network. And here, as you can see, the basic purpose is to distribute the broadcasted video signals to residences. That means, the TV signals which are received through an antenna. Here is an antenna which is usually installed on the top of a roof, that receives the TV signal sent through satellite, and then a device is used which is known as head end, and head end is responsible for distributing the signal on a cable network. And this cable distribution system, as you can see, can have a number of amplifiers, because the signal strength goes attenuated as the signal goes from the head end towards the residential complexes. So, you can have a large number of amplifiers. Then with the help of a splitter, the coaxial cable is divided to distribute in a big residential campus, and here, as you can see, a drop cable is used which taps from the distribution cable, the coaxial cable, and takes it to the residences. So, this is the overview or the schematic view of the standard cable TV system. And as we have mentioned, the cable TV system uses the coaxial cable compared to the DSL technology, which uses the twisted pair. So, in cable TV we find the widest use of coaxial cable, and as you know, the coaxial cable provides much better immunity to interference and crosstalk compared to twisted pair. So, it gives you a better bandwidth compared to cable modem. As you have seen, while discussing the cable it will not be cable modem, it will be essentially the DSL network. As you have seen in DSL network, the twisted pair is used and the actual bandwidth is much less than the highest possible bandwidth that is possible. That means the bandwidth of the twisted pair is not fully exploited because of the noise, interference, crosstalk and so on. So, the actual bandwidth available is restricted, and as a consequence the overall available bandwidth is much less, and obviously coaxial cable used in your cable TV system provides you a better alternative and it gives you higher bandwidth. And the bandwidth of the cable TV system use the frequency range from 54 to 500 megahertz. So, this is the frequency range that is being used for cable TV system and which is used for distributing the large number of TV signals from different stations. And there are two standards. One is your NTSC, that is your National Television Standards Committee, and another is phase alteration by line PAL standards, which uses 6 megahertz and 8 megahertz bands respectively. And since it uses 6 megahertz and 8 megahertz bandwidth, and this 54 to 500 megahertz is distributed over a number of channels, providing 50 to 70 channels depending on whether you are using NSTC or PAL standards. Depending on the standards used, the number will be different. For example, if NSTC is used, you will get about 70 channels, and if PAL is used, you will be getting about 50 channels because you require higher bandwidth per channel. So, these are the two popular standards, and as you have seen in the diagram, there are three important devices used in cable TV devices. The first one was the head end. The head end receives the video signals from the broadcasting stations with the help of an antenna installed at the top of a tall building. As you have seen in this diagram, here I have shown a tower. It need not be a separate tower, it can be this antenna can be mounted on the roof of a building, and from there the electrical signals is amplified and goes to the head end, and from the head end it is distributed over the coaxial cable. And so video signal after receiving it is distributed on the coaxial cable. Then, as I have mentioned, you require amplifier to boost the signal, because as you know the coaxial cable has high attenuation. So, as the signal goes from the head end towards the residential buildings, it gets attenuated. So, to improve the signal level, you have to use amplifiers. To boost up the signal level, you have to use amplifiers, and you can use up to 35 amplifiers in cascade between the head end and the subscriber premises. So, a large number of amplifiers may be required to provide service to a large number of buildings, to a large number of users. Then you have got splitters. Splitters are used to split distribution of signals into branches. So, with the help of these splitters, a single coaxial cable, from a single coaxial cable you can have, say, a single coaxial cable has come, from this you can have two coaxial cable and so on. So, you can have branches with the help of splitters. Then from the drop cable you can make a tap, some kind of tap, and from that tap the drop cable goes to residential buildings, that means the user premises, subscriber premises. So, this is how the cable TV system works with the help of three devices. And as I mentioned, because of large attenuation, you will require a large number of amplifiers, and this restricts the communication unidirectional. That means only the downstream signal goes from the head end to the residential premises. So, the signal transmission in cable TV, standard cable TV system is unidirectional. So, only the downstream signal is present. Essentially, the TV signals are distributed over the residential buildings with the help of this cable TV system. To overcome this limitation, the cable TV system has been extended, which is known as hybrid fiber coaxial network. Here, as you can see, a combination of fiber optic and coaxial cable have been used. So, here there is a regional cable head, RCH regional cable head, where the signal is picked up with the help of a picking antenna, again with the help of a tower, or the antenna is put on the top of a building, tall building, and from there the signal goes to distribution hubs. So, distribution hubs, from the distribution hubs to the phi 1 node, it is essentially optical fiber. So, you can see here in between there are switches, and with from the phi 1 node it is essentially coaxial cable. So, we find that ultimately to the user premises it is nothing but coaxial cable, but in between from the distribution hub to the phi 1 node it is the optical fiber. And because of the use of optical fiber, you can have lesser attenuation, and as a consequence you will require a small number of repeaters or amplifiers, and as a consequence you can use bidirectional communication. So, now you can have bidirectional communication, and not only that, because of very high bandwidth of optical fiber, it is possible to serve a large number of users. As you can see, a single regional cable head can serve as many as 400,000 users. So, from here the distribution from here it can come to that RCH, it can go to several distribution hubs, and altogether 400,000 users can be served, and from each distribution hub one can from each distribution hub 40,000 users can be provided service. On the other hand, each coaxial coming out from the phi 1 node can be used to serve about 1000 users. So, you can see there is a hierarchy of the optical fiber cable distribution, and this is how it is done is shown in this diagram. Here, as you can see, this is the optical fiber cable, and as you can see there are two cables, one is upstream fiber, another is downstream fiber. So, you require a pair of optical fiber cable for bidirectional communication. So, you have upstream and downstream fiber cables. Of course, when the length is long, you will require some amplifier, but the number of amplifiers required will be much smaller. There we have seen the number of amplifiers required is 35. Here it can be restricted to 5 or 6 or 7, not more than that. Then from the phi 1 node the signal is distributed using coaxial cable, and whenever necessary to amplify you will require bidirectional, it will be a bidirectional split band amplifier. So, you can see with the help of several bidirectional split band amplifier the signal is distributed in the residential premises. So, a large number of users, each such coaxial cable can serve as many as 1000 users, as you have seen in the last slide. So, 1000 users can be served. So, this is the coaxial distribution plant ultimately going to the residential premises. Here is the taps taken from the coaxial cable, and these are the bidirectional split band cables, split band amplifiers. So, this is the overall network for HFC system. Now, let us look at the bandwidth distribution of HFC, hybrid fiber coaxial cable system. In case of standard cable TV network, we have seen you have got only downstream band, that is from 54. So, from 54 to 550 megahertz. This was the bandwidth used in cable TV system. So, it was only downstream which can support about 50 270 channels. But here we find we have got 3 distinct frequency bands. We have retained the video band, that is downstream frequency band used for video distribution. In addition to that, there are 2 data bands, one is data upstream and another is data downstream. Data upstream band is from 5 to 42 and data downstream is from 550 to 750. We observe that the upstream bandwidth is much smaller than the downstream bandwidth. You may be asking why the upstream bandwidth is smaller than the downstream bandwidth. Usually it is used for internet service. Now in internet service it is used for providing internet service to the residential users. So in such cases usually the data which is going from the users to the internet is small. On the other hand, large volume data flows from the internet to the users. As a consequence, you require higher bandwidth for downstream data compared to upstream bandwidth. That is why we will see the upstream bandwidth is smaller compared to downstream bandwidth, and the similar situation we have seen in DSL technology also. Now we see how the bandwidth distribution takes place and how it is being utilized. First we consider the upstream data band that occupies the lower band 5 to 42 megahertz, which is divided into 6 megahertz channels. So since it is 5 to 42, we will have only 6 channels, and each of these 6 channels will have 6 megahertz bandwidth, and as it is more susceptible to noise, QPSK is used for modulation purpose instead of QAM, because amplitude modulation as you know is prone to error whenever there is noise. So since it uses QPSK, you can have only 12 megabits per second bandwidth. That is the theoretical data rate possible is 12 megabits per second, because QPSK as you know gives you a baud rate of, for a baud rate of, whenever you use 6 megahertz bandwidth channel, you can go your data rate will be 12 megabits per second multiplied by 2. That means pass signal element you can send 2 bits of data. That is how you get this 12 megabits per second. Although this is the theoretical maximum data rate, actual data rate in the downstream upstream direction will be much smaller, because you cannot really achieve this 12 megabits per second bandwidth. Then the video band, that is downstream only, that is used for 54 to 550 megahertz. It can accommodate up to 80 channel, as you have seen. Since each channel requires 6 megahertz, you can have at most 80 channels, about 80 channels can be transmitted, that is for video band. On the other hand, the downstream data band occupies the bandwidth band from 550 to 750 megahertz, and which is divided into 6 megahertz channels, and it has got about it will have about 33 channels, not 80, 33 channels. It will have about 33 channels, and by using modulation, that 64 QAM modulation, it can give you, since you are using 64 QAM in the downstream data, you can transmit 6 bit per signal element, that gives you 6 into 6 36 bits per signal element. However, or the 36 megabits per second. However, 1 bit is used for upward error detection, and that is how the theoretical data rate is 30 megabits per second. However, in practice the actual will be 12 megabits per second. You may be asking why the actual data rate is 12 megabits per second. The reason for that is the cable that is being used for this downstream data is essentially that 10 base T twisted pair cable, and with the help of that you can support only 10 megabits per second. as a consequence the actual data rate will be much smaller. So, these are the we have seen how the 3 bands are used and how they are modulated by using QPSK and QAM. And obviously, the data that is being sent either upstream in downstream direction are shared. The subscribers share both upstream and downstream bands. As you have seen, the HFC can support a large number of subscribers, 400,000 from a single cable head, single regional cable head. So, obviously, over the band the bands have to be shared. So, as the upstream bandwidth is only 37 megahertz, these are divided into 6 megahertz bands, as I have already mentioned, and that is done by using frequency division multiplexing, and these 6 megahertz bands can be shared by a number of users. Actually, one channel is allocated to a group of users either statically or dynamically. We shall see how this upstream band is shared, how a particular channel can be used by a particular subscriber at a particular instant of time. That means, you have to use some kind of time division multiplexing. This is called actually TDM, time division multiplexing, and essentially it uses some kind of medium access control technique. We shall see how this can be done later on. Then the downstream sharing is also done, because you have got only 33 channels, each of 6 megahertz bandwidth, and these are shared by all the users. Of course, here the contention is not required. There it is essentially multicasting. The signal is coming from the network, maybe through optical fiber cable, then it is distributed over a large number of users, and based on the address the signal is diverted and multicasting is used. So, that means, here multicasting is done based on matching of address. So, the different signals, different channels goes to different user based on the address, because each user is provided with an address whenever he gets the HFC service. So, here are the different devices that is used in cable modem system. So, here you see the cable modem that is being used in the residential premises. This is the customer residence, and this is the coaxial cable, and a tap is made. From there the signal comes to a filter which separates out the video signal. That video signal will go to a television, and the data signal will go to a cable modem, which will do the necessary modulation and demodulation, and the signal will go to a computer. So, here it is going to a computer. So, you can see here both data as well as video communication is possible by using this device. Now, let us look at the system used in distribution hub. That cable modem transmission system, or CMTS, is installed in the distribution hub of the cable company. This is in the cable company. Here we see the signal comes from the optical fiber. There, in the previous case, it was essentially coaxial cable that goes to the residences, but here the optical fiber is going to the distribution hub, and from the distribution hub, as you can see, it is bidirectional, a pair of optical fiber where we have seen that upstream and downstream fibers are there, and these two signals are coming. One is coming from the head end, and this is going to it is coming from the head end, the video signal, and this signal is coming from the internet. It is, as you can see, it is a bidirectional signal which is going to the CMTS, and that it is combined here, and that goes to the fiber. That means the signal which is downstream is combined, which goes to the user, and the signal which goes to the internet comes in this direction, and it goes to the internet. So, this is how the communication takes place. That means, CMTS receives data from the internet and sends them to the combiner, this is the signal, and it also receives data from the subscriber from here and it passes them to the internet. So, that CMTS does communication in both directions. Let us see the data transmission scheme used in cable TV system. As I have mentioned, the cable TV system allows you data communication. You can have both voice, video and data can be sent. You can have video on demand if necessary, and how it is being done is explained here. It uses DOCSIS, the data over cable system interface specification devised by multimedia cable network system. So, MCNS developed the DOCSIS for the data transmission for the purpose of data transmission over cable modem. DOCSIS defines all the protocol necessary to transport data from CMTS to a CM. Time sharing is allowed for upstream data. As I have mentioned, the upstream data has to be time shared. A cable modem must listen for packets destined to it on an assigned downstream channel. That means, a channel is assigned, and obviously assignment is done based on some kind of contention. The CMs must contend to obtain time slots to transmit their information in an assigned channel in the upstream direction. That means, it is some kind of contention based medium access control. Later on we shall discuss about in more detail when we shall discuss the local area network. There this kind of technique is used, and so a cable modem has to contend for a channel, and once it gets it, then the CMTS will be able to send data and it obtains time slot to transmit data. That means, it is a combination of FDM and TDM is used here for the transmission of data from a large number of users. Then the CMTS sends packets with the address of the receiving CM in the downstream direction without contention. As I have mentioned, here it is some kind of multicasting. So, there is no need for contention. With the help of the address assigned to a particular subscriber, the signal can be diverted to different users. So, this is the data transmission scheme in nutshell used in cable TV system. Now, we shift gear to discuss about another important application of multiplexing, that is SONET. As the need for higher data rate is growing, it is necessary to utilize the enormous bandwidth of optical fiber. As you have seen, optical fiber provides you very high bandwidth, and to utilize it fully, it is necessary to have standard, and two standards have been developed. One in US, developed by American National Standards Institute, ANSI. ANSI developed a standard known as synchronous optical network or SONET. On the other hand, in Europe, another very similar standard was developed by ITUT, which is known as synchronous digital hierarchy, or in short it is known as SDH. These two are very similar, and they have three important features. First one is, it is a synchronous time division multiplexing system controlled by a master clock, which adds predictability. So, it is a essentially network wise synchronous system, and because it is synchronized by a master clock, it is very predictable and dependable. And as you have seen, that synchronous communication, as we shall see in the next class in more detail, that synchronous transmission, synchronous communication requires lesser, has more efficiency. We have already discussed when we discussed about that synchronous time division multiplexing and asynchronous time division multiplexing. We have seen that asynchronous time division multiplexing requires higher overhead. So, since this SONET uses synchronous time division multiplexing, it is quite efficient, and it has, so the overhead is much less. Second important feature is different manufacturers follow standard. The standards which have been developed are being used by a number of optical fiber system manufacturers. So, we get standard based equipment for use in SONET system. Thirdly, this it has been designed to allow carry signals from incompatible tributary systems. In the last lecture we have discussed about the telephone network. There we have seen that DS, digital signal system, have been developed. That is a hierarchy of signals that is used in telephone network, but their bandwidth is smaller. So here we shall see that those signals, those DS signals, can be also sent through this SONET network. Because of this, SONET is becoming increasingly popular and widely used. Here is the schematic diagram of a SONET network. Here we see there are three different types of devices: STS multiplexer, regenerator, and add drop multiplexers. So these are the three different types of devices used here. Electrical signals coming from different users are coming to the STS multiplexers, and then it is converted into optical signal. So here it is electrical and it is converted into optical signal with the help of STS multiplexer. The optical signal goes through, and if necessary it is regenerated with the help of regenerator, which is nothing but amplifiers, some kind of amplifiers. That optical signal, the noise is removed and it is regenerated, and in fact it does more than that, as we shall see. And from the regenerator it goes to add drop multiplexer. Here it is another kind of multiplexer, not same as the STS multiplexer. The optical signals can be picked up or combined and then sent through optical cable, and then it goes to another add drop multiplexer if necessary, and if the distance is long you will require one or more regenerators before it goes to the STS multiplexer, and it goes to the other end where again it is converted into electrical signal and goes to the users. So between two users you have got STS multiplexer. So in the simplest case you need not have regenerator, need not have a add drop multiplexer. Essentially STS multiplexers can be directly connected if the distance is small. However, if the network is complex, you will require a large number of STS multiplexers, regenerators, and add drop multiplexers. So we have seen the three different types of devices used in SONET. What are the functions of these three different types of devices? Let us see. First one is the synchronous transport signal multiplexer demultiplexer. So it either multiplexes signal from multiple sources into a STS signal. STS signal, as we shall see, it is a hierarchy of signals, or it demultiplexes an STS signal into different destination signals. So here it gets converted from electrical to optical or from optical to electrical. So both these conversions are done in these STS multiplexers, and so a number of electrical signals are combined and then sent in the optical form, or a number of optical signals are received by the STS multiplexers and converted into electrical signals to be sent to different destinations. Then you have got regenerators. It is a repeater that takes a received optical signal and regenerates it, removes noise and regenerates it. Its functions in the data link layer. So it does something more than simply regenerating the signal. As we shall see, it will add some information, it will take out some information, add some information in the frame. So that is why it works in data link layer as well as in your data link and physical layer. Then you have got add drop multiplexer. Add drop multiplexer can add signals coming from different sources into a given path, or remove a desired signal from a path and redirect it without demultiplexing the entire signal. So the demultiplexing and multiplexing is restricted to the STS multiplexers. On the other hand, the add drop multiplexer can divert path or remove a desired signal from a path. It is done based on address and pointer, as we shall see. and the sonnet has got 4 different layers. We have earlier discussed about the 7 layer OSI model, and we have seen the functions of different layers. Here the sonnet is divided into 4 different layers to divide the complexity. As we have seen, whenever the complexity of a system is very high, it is divided into a number of layers. So here also the sonnet is divided into 4 different layers. First one is known as photonic layer. Photonic layer corresponds to the physical layer of the OSI model, and here it performs the function of that it works in energized form, energized encoding is used, and it does on off keying. So it does the on off keying modulation, that means when there is 1 then optical signal is present, and when it is 0 no signal is present. So O corresponds to no optical signal and 1 corresponds to when there is optical signal. So that is essentially on off keying used modulation. The section layer is responsible for movement of signal across a physical section. It performs framing, scrambling and error control. So the section layer does performs the 3 different functions. It and also it is responsible for movement of signal between across a physical section, as we shall see what we mean by section. Then the line layer is responsible for movement of signal across a physical line. STS multiplexers and add drop multiplexers are provided with line layer functions. That means the regenerators do not have this line layer functions. On the other hand, the STS multiplexers and add drop multiplexers are provided with this line layer functionality. Finally, it has got path layer. This is responsible for movement of signal from optical source to optical destination. STS multiplexers are provided with functionality of this layer. Only the STS multiplexer is provided with this functionality. Let us see what is the relationship of this 4 layer sonnet model with the ISO's OSI layer. We know that ISO's OSI layer has got 7 layers. The lower 2 layers are physical and data link. So the photonic layer belongs to the physical layer, where it decides the signal level, distance and all these parameters for physical transmission of optical signal. So that is done in the photonic layer. On the other hand, the data link layer has got 3 different sub layers. That means all the 3 layers of the 3 upper layers of sonnet belong to the data link layer of the OSI model. That means path layer, line layer and section layer, all these 3 belong to data link layer. And here, as you can see, the functionality is incorporated in different devices of the sonnet system is shown here. The STS multiplexers are provided with the functionality of path, line, section and photonic layer, all the 4 layers. On the other hand, the regenerators are provided with only the functionality of 2 layers, photonic and section layer. Since it has got the functionality of photonic and section layer, that is why we say that regenerators belong to both physical as well as data link layer. On the other hand, the add drop multiplexers has the 3 layers, photonic, section and line layers, and the STS multiplexer, as we have already mentioned, has got 4 different layers, photonic, section, line and path layers. Here let us see what do we really mean by section, line and path. Between any 2 devices, between 2 regenerators, this is one regenerator, this is another regenerator. Between any 2 regenerator, it is a section. Between the regenerator and the add drop multiplexer is a section. Between the add drop multiplexer and STS multiplexer is a section. That means between any 2 devices a section is formed. On the other hand, between the line terminating equipment or between two line terminating equipment, or between path terminating equipment and line terminating equipment. Path terminating equipment is essentially the STS multiplexer, line terminating equipment is essentially the add drop multiplexer. Between each of them forms a line, and the end to end, from user to user, the electrical to electrical, optical, that means the when it is converted from optical to electrical and electrical to optical to electrical to optical and optical to electrical, it is essentially a path. So, this is essentially end to end is the path. Between a path you may have several lines, and between each line you can have several sections, as it is depicted in this diagram. Now, as I have mentioned, a hierarchy of signal levels called synchronous transpose signals are defined, and these synchronous transpose signals has a hierarchy, just like that DS signals we have seen in telephone network. Here, as you can see, you have got STS1, which has raw bandwidth of 51.84 kilobits per second, STS3, which is 3 times of that, has got 1.54, and up to you have got STS192. However, that STS1, STS3, STS12 and STS24, these 4 are the most popular hierarchical levels commonly used. So, the raw data rates, electrical data rates are given here in this third column, starting with 51.84 megabits per second, and as you can see STS192 has got 9953.28 megabits per second. So, you see it is very high data rate that is supported by optical fiber SONET network. The electrical signal, this is called the services, and it is converted into optical signal, and which is sent by optical carriers. So, this is your optical carriers. STS1 is converted into optical signal corresponding to OC1. So, optical carrier 1 carries the STS1 signal, OC3 carries the STS3 signals, and so on. So, in this way, here you have got the physical levels used to carry the signals are called optical carriers. So, these are the optical carriers used. Now, so although this is the raw the third column gives you the raw mega bandwidth, the megabits per second of the synchronous transpose signals, there are overheads. First of all, as we shall see, out of this in this STS1, out of this 51.84 megabits per second, this is your that envelope, that synchronous payload envelope is only 50.12 megabits per second, and out of which there is some overhead like section, line, of course path overhead is covered here, that in the SP, or the some overheads are there, and if you exclude these overheads you get the payload of only 49.536 megabits per second. So, this is the actual payload that you get from the SONET system. So, as you can see here, the overhead is not really very high. So, 51.84 and this is 49.536. The overhead is about 2%, 4% I believe. It is about 4%, which includes the overhead of all the layers that we shall see. So, this is the basic STS1 frame format at the photonic layer. So, here as you can see, you can transmit a single STS1 frame comprises 8000 frames. So, one after the other these frames are sent, frame 1, frame 2, then frame 8000. On the other hand, each frame is divided into 810 octets, and each octet has got 8 bits. So, a single frame comprises 6480 bits, and this 8000 frames are sent per second. So, your data rate is 51 51.840 51840 bits per second. That means your 51.840, it will be 51.840 megabits per second. So, here as you can see, a single frame is shown where you have got the that 810 octets, as you can see here. Per row it has got 90 octets, and out of which first 3 columns are used for overhead, section and line overhead. The upper 3 rows, the top 3 rows of the first 3 column gives you the section overhead, and the first 3 columns, I mean this 6 rows of the lower first 3 columns is the line overhead, and the path overhead is 1 column. That means you have to exclude 4 columns which are essentially overhead, and if you exclude from 9 to 1 90 octets, you get 87 octets, which is known as that synchronous payload envelope SPE, out of which 1 is used for path overhead, giving you user data of 774 octets. So, you have got 9 such rows of 90 octets per row. Now, this gives you in more details. This is the section overhead, that is your 3 rows, and here you have got 6 rows, 3 columns and 3 rows, and 3 columns and 6 rows, and here 1 column for path overhead. So, section overhead, line overhead and path overhead. So, that means when the electrical signal comes, it goes through first the path overhead, then the line overhead, then the section overhead. All the overheads are incorporated in a frame, then it is converted into optical signal and transmitted in the optical form. Now, those STS signals can be combined to form higher order signals. For example, 3 STS1 signal can be combined with the help of multiplexer to form STS3 signal, and in general we can have STSN frame format, where as you can see, this is the overhead bits, overhead columns are provided at the front, which has got 3 into n columns, and remaining are 87 into n are essentially the payload, of course, as we know, out of which there are path overheads present here, which is not shown here. So, this is how the multiplexing can be done, and you can create the different types of hierarchical signals. And so, here as you can see, again 3 STS1 signals have been combined to form a STS3C concatenated signal. So, overhead columns are here, and the payload 1, payload 2 and payload 3 columns are combined to have a concatenated payload, and this can be sent through the optical network. Now, question arises, is it possible to send the DS signals used in telephone network through the SONET network? Yes, and we shall discuss how it is being done. And as we know that digital signal service used in telephone network has got a hierarchy of digital services. DS0 service is similar to DDS, a single digital channel of 64 kilobits per second, and as you know, DS1 has got 1.544 megabits service, DS2 has got 6.312 megabits per service, DS3 has got 44.376 megabits per service, and DS4 has got 274.176 megabits per service. And as we know that T lines are used to implement these services. Now, as you can see here, even the DS3 bandwidth is lower than the STS1 signal. So, how we shall send DS1, DS2 and DS3 signals? For that purpose, a technique known as virtual tributaries have been created, and let us see how we can send those DS signal through the SONET signal by using these virtual tributaries. So, to make SONET backward compatible with the current hierarchy, the frame design includes a system of virtual tributaries. Four types have been defined, 4 types of tributaries have been defined. One is VT 1.5, this is used to accommodate DS1 service, which is only 1.544 megabits per second. As you know, this can accommodate 24 voice channels, and VT2, which can accommodate European CPT1 service, which has bandwidth of 2.048 megabits per second. VT3 can accommodate one DS1C service having bandwidth of 3.154 megabits per second. VT6 can accommodate DS2 service 6.312 megabits per second, and more than one tributaries can be overlapped column by column, and this SONET provides the mechanism to identify each virtual tributary and separating them without demultiplexing the stream. That means, based on the pointers and addresses, those VT signals, virtual tributaries, can be separated out and can be sent to proper destination. So, here the virtual tributaries are shown. This is VT 1.5. If you multiply 1.5, you get 3. That is why it has got 3 columns, and it has got, as you can see, 1.728. Of course, this is 1.728. However, it is sending only 1.544 that DS1 signal, and others are essentially overhead. There are overheads here, and similarly the other 3 tributaries, VT2 has got 4 columns, VT3 has got 6 columns, and VT6 has got 12 columns. These can be interleaved in a single SONET frame, STS1 frame, for transmission through the optical fiber. So, friends, we have discussed 2 important applications of multiplexing in this lecture. One is that cable modem, another is SONET. Here is time for the review questions. First one is distinguish between the services provided by the cable TV and HFC networks. Second question is how the upstream bandwidth is shared by a group of users for data transfer in HFC network. Third question is how is an STS multiplexer different from an add drop multiplexer. Fourth question is what is the relationship between STS and STM. Fifth question is how does SONET carry data from DS1 service. These questions will be answered in the next lecture, and it is time to answer the questions of the previous lecture, that is lecture number 12. First question was distinguish between analog switch service and analog lease service. As you know, analog switch service is the commonly used dial-up service. On the other hand, before data communication is performed in this dial-up service, you have to establish the connection. It is a common experience to us. First of all, we dial a number, establish a connection, then you transfer data. On the other hand, in lease service, dedicated link is always exist, irrespective of whether any data is sent or not. So, there is no need for establishing a connection. Connection is already established. Second question was if a single mode optical fiber can transmit 10 gigabits per second, how many telephone channels can one cable carry? As we know, 1.544 megabits is required to send 24 telephone channels using pulse code modulation. So, 10 gigabits per second will allow to send 15,440 voice channels over an optical link. You can do the calculation, you will find that considering 24 channels per 1.544, you will be able to send 15,440 voice channels through a 10 gigabits per channel in an optical fiber. So, you can see large number of voice signals can be sent through a single optical fiber. Third question was how DSL provides broadband service over local loop. As we know, the twisted pair is used in local loop, which has the bandwidth of 1.1 megahertz. So, by using suitable modulation technique, it is possible to provide broadband service over local loop of the telephone network that we have already discussed in detail. So, the filters that is commonly used in telephone network is removed, and with proper suitable modulation technique, it is possible to provide that broadband service in DSL. Why the actual data rates available through DSL line is substantially lower than maximum possible rates. As we have seen, although the maximum data rate is high, but the because of the long length of cable, attenuation, quality of cable, signal to noise ratio, it is not possible to send at that maximum rate. So, the rate data rate that is required that can be sent is decided dynamically based on the line condition in DSL network, and usually it is much lower than the maximum network. So, friends, in the last two lectures we have discussed 4 important applications of multiplexing. First, we have seen the application of multiplexing in telephone network, then we have seen the application of multiplexing in DSL technology, which provides broadband service, and third application we have seen in cable modem, and fourth one is SONET, and all these are very popular and widely used for data communication. Thank you.